Okay, good afternoon everyone. We will continue with the discipline researcher in the center with Prasun. He will speak about criticality theory and Hardy inequality.
Thank you. Thank you for the introduction. Thank you to the organizer and thank you, Professor Michael, to give me an opportunity to talk about something called about my work. But I will say criticality theory and Hardy inequality is a kind of they are related to each other, and these two things motivate in my work. Maybe today in this short talk I will not be able to present what are the details of my work, but it's rather than the motivation towards that work. Okay, so my primary goal would be to introduce criticality theory and what is Hardy inequality, those two things, and how they are related to each other. And in the middle of the talk, you may find that this Hardy inequality, something related to Hardy weight, and it's not known, or it will not be the just known Hardy weight, which is like the singular potential 1 over mod x square with the Hardy constant. So it might be something general weight. Okay, so here is my plan. Like first I will give an overview regarding Hardy inequality and something on Poincare inequality also, then criticality theory, and if time permits, then I will go to the applications of those two things regarding the improvements of inequalities. Okay, so here is I am starting with the Hardy inequality, and in 1921 this theorem was proved. Something it's not Hardy, it's Landau. So this is the discrete version of Hardy inequality, and actually. This inequality was separately proved by Hardy, but the story is different. Hardy, in some paper in 1925, he mentioned that first he got the proof of this discrete inequality with base constant from a letter of Landau, and that's why some mathematicians call it just Landau inequality. But Hardy later realized that he was trying to solve something, he was trying to give some different proof of called Hilbert's double series, convergence of Hilbert double series, and later he realized that in that paper or in that article he already proved this inequality, and so there is a good story. And okay, so and in 1925 Hardy proved it by himself the one-dimensional version or continuous versions of this of the discrete inequality, and I just mentioned the double series sum that was prescribed by Hilbert on 1906 actually, and in between 1906 and 1928 there are many different angles towards the Hardy inequality, and here is one monograph, one can say, by Kufner, Melker, and Pearson, which one can see this paper for a detailed discussion in the entire this 20 years or more than. Okay, so but in today's talk I will be mainly focusing on the multidimensional version. So this is the multidimensional form of Hardy inequality, and why this inequality is special? Because see, here is something singularity is there, right? So it says that if some functions, if it says the L2 norm of the gradient is bounded, then that singular term u over mod x, the L2 norm of that singular term, we can still bound. That is the strength of Hardy inequality. Okay, and of course this constant a minus 2 square over 4, this is Hardy constant, this is base constant. And what is the meaning of base constant here? The meaning is like we cannot replace this constant by something bigger one. So that is the meaning of base constant. Okay, and so here dimension starts from 3, right? So of course one can put n equals to 2. So something non-negative term which is greater equals to 0, that's still true. But if we ask something more about this Hardy weight, like on entire R2, does there exist any potential which not necessarily be like 1 over mod x square? So the question is, does there exist any non-negative potential for which on entire R2 this kind of inequality holds? The answer is no. Like if such kind of things holds, then V has to be identical 0. And the reason behind that is the criticality theory. So here the criticality theory starts like and okay, and yeah, so in dimension 2, yes.
Basically, or it's like difference between those cases. So basically, in the first case, you remove the origin and then can divide by x squared, and so you allow the origin. The effect is the same, right?
Yes, actually, here also we need to like because I will explain like that operator Laplacian is critical on a punctured domain. So in that way, okay. So okay, now let me go to the generalization of the Hardy inequality on Euclidean setting to the manifold case. And in 1997, Carroll gave that generalization on the Riemannian manifold case, and this type of Hardy inequality holds true. And yes, not for every Riemannian manifold, a Riemannian manifold will satisfy some geometrical conditions like the Laplacian Laplace-Beltrami operator on the distance function. If that is bounded below by that C over rho, then we have this kind of, and that C is the same. So then we have the Hardy inequality. Okay, so what happened for the Euclidean case? In fact, one can check in the Euclidean case, the Laplacian of the distance function will be exactly n minus 1 over the distance function. So C will be n minus 1, and we can easily get back our Hardy inequality, right? With the n minus 2 over 2 square constant. Okay, and what are other examples which satisfy this kind of criteria? Other example is called so-called like Katal-Hadamard manifold, which has like everywhere non-positive curvature, sectional curvature, which is complete simply connected. So there are other examples. Okay. Okay. Now let me give about some details about the Poincare inequality. The Katal-Hadamard manifold, which has whose sectional curvature is bounded by a strictly negative constant. For those kind of manifold, we know like Poincare inequality holds. And what is Poincare inequality? Like there exists a positive lambda for which this kind of inequality holds true. Example, hyperbolic space. We know for hyperbolic space, the sectional curvature is always minus 1. So then one can check the Poincare inequality holds true. In fact, one can compute this lambda. And this lambda actually, if we consider the Rayleigh quotient, then this n minus 1 square over 4, this will be that lambda. And in the literature, it is known as Poincare constant. Okay, but here important part to note, like this constant is never achieved. Never achieved means we don't have any h1 functions for which, if we compute the ratio, that will be exactly that value. Okay, so that is the meaning of never achieved. And whenever we have this kind of phenomena like never achieved constant, that means there is always a scope of improvement. And I'll precise what is the meaning of improvement I'm talking about. Okay, and if we just have a look on this kind of Poincare inequality on entire Rn, that is not true. On entire Rn, this kind of Poincare inequality not true. Of course, on bounded domain, situations are different. There, of course, we have Poincare inequality by taking some average, all those things are there. But on Rn, not true. Okay. Okay, so I'm interested in this kind of improvement. So this is Poincare, right? This is Poincare inequality. Now question is, does there exist any potential V for which we can, non-negative potential of course, is there any V for which we can add this term? Is it possible to have this kind of improvement or not? So I am interested in this type of improvement. And again, same thing one can ask for the Hardy inequality also. Is it possible to add this kind of V or not? So these questions, in this type of questions I am interested. And the next part will be, suppose such V exists, okay? So the question is, does there exist anything bigger than that V? So like any suppose some we can find some V. The question would be, what is, are there anything V which is bigger than our first one case? So there is always a questions. So what is a large weight there? That kind of questions one can immediately ask. And again, suppose we have some V, then just insert that V into the left hand side of this inequality and ask same question, like, is it possible to do same thing again, like, is the inequality further improvable or not? So of course, if possible to add this kind of weight, then the question is the optimal one or something like that. So we need to phrase this phenomena in a good manner, in a well-defined way. So that's why the criticality theory comes to the picture, and something we will call the optimal weight. And that might not be the Hardy weight. We say it's the optimal Hardy weight, and that might not be the just singular potential 1 over mod x. So that could be anything general. Okay, so let me go to that direction. Okay, suppose P is some second order non-negative elliptic operator with reasonable smooth coefficient. Okay, then we say P minus V, that operator is non-negative, where V is some non-negative weight. If this thing holds, this inequality holds, what is this Q? This is the quadratic form. Just take this P minus P, do the inner product, use some, if we have some Laplacian, use the by parts, the gradient, that quadratic form, that is this Q. So if this thing holds with this V U squared, then we will say P minus V is non-negative. Okay, now I am giving the definition of critical operator. So a non-negative operator, P minus V, that means P minus V is greater or equals to 0, which means this inequality holds. Then we call that P minus operator is critical if just V is the highest one. Like there will not be any W which is bigger than V, and P minus W will be greater or equals to 0. Okay, so if these things happen, like if V is the largest one, and largest in a sense, if we have just at least a single point, like point-wise largest, I'm defining meaning. Okay, so if we have this kind of V, then and with P minus V non-negative, otherwise if that is not non-negative, then we will not have the inequality. Okay, so then we will say that operator is critical. Okay, and regarding criticality, critical operator, this is some definitions of minimal growth. And okay, so okay, let me define what is minimal growth. We say some functions, some solutions on the near of infinity is minimal growth if that is the minimal one. What is the meaning like that? Like say consider another functions in the neighborhood of infinity. On the boundary, if that function is bigger than this u, then it has to be like minimum in the entire thing. That is the minimal growth. Like near infinity, it's the minimum solution. That is the main thing. And this kind of functions is very much interesting to check the simplicity of eigenvalue. This kind of functions are useful, this minimal growth. And in fact, we call this minimal growth as Agmon ground state. So, okay, and okay, now example. If we consider the Laplacian operator on R2, then we can check the one function will be the Agmon ground state, and there is the theorem by Pinchover, like if some function is critical operator, there has to be some Agmon ground state. So he proved the equivalence of two things, and one is the ground state for Laplacian on R2, and yeah, so that's why Laplacian operator on R2 is critical operator. And so critical means here we cannot expect any non-negative potential. So so earlier I mentioned that kind of V not exist, so that answers here. Okay, so now let me go to some construction of Hardy weight. Okay, suppose some operator is not critical, then we say it's subcritical, and precisely we define a subcritical operator when it admits some positive minimal Green's function. And again, the minimal in a sense just pointwise minimality. So now the question is, suppose we have subcritical operator, that means that operator, corresponding with that operator we have some Green's function, minimal Green's function. The question is, say that the notation of that Green's function is GPM, like on some manifold M, and P is that operator, say GPM is the Green's function. The question is there any method to calculate that W? So what W I'm talking about, like earlier I mentioned, P minus W is critical operator. So the question is there any method to get or to construct that W for which P minus W will be critical? Like further improvement is not possible. Is there any recipe? That is a question. And recently, actually, not recent actually, maybe 5 years, yeah, actually 8 years ago, these questions were understood completely. In the work of Devier, Frost, and Pinchover, he proved or he gave this kind of method to find out that weight. So yeah, if G is the Green's function and U is some solutions near on the manifold, and it satisfies these kind of limiting conditions, then from this theorem we can see this W is that critical weight, like that optimal Hardy weight. So what is the meaning of again that optimal Hardy weight? Like this expression, P minus W is critical. So of course critical means non-negative conditions is always there. So we will immediately get the inequality, but the story ends here in a sense. Further improvement is not possible. Further improvement means that kind of improvement, integral V U square, finding more V, that is not possible. Okay, now let me give some example. Okay, so consider Laplacian operator dimension 3 onwards. We know like this is with some constant, this will be the Green's function, and we can check the other conditions also. Then if we substitute everything in this recipe, then we can immediately see this will be the weight, this will be the W, optimal weight. And what is this? This is nothing but known Hardy weight. That means this operator is critical operator. So, and this will be the Agmon ground state correspondingly to this critical operator. So this gives like Hardy inequality, like the multidimensional version of Hardy inequality on Rn n greater or equals to 3 is not further improvable on entire domain, but on bounded domain the stories are very, very different. The starting work of in 1997 by Breizes-Voskov, improving by using some kind of roots of Bessel function. Starting from there are plenty of paper, many authors try to give improvement in a different directions, but on Rn, that's all. It's not possible to improve. Okay, so and what about LP versions? Yes, in 2016, Devier and Pinchover, they give construct this kind of story, this kind of criticality, all those things for the LP version also. Here, I just told the P equals to 2 case, and one can see in 2018 for the discrete case also that things are already discussed. Like discrete case, one-dimensional. Discrete case, LP version, everywhere the Pinchover and et al, they have already provided what is the optimal thing. Like all those possibility of improvement has been done. Like they give the end of the stories. Like one cannot expect further improvement or not. Okay, so that seems like something end of this the improvement of inequality, but actually not. In the theory, it's a very general theory. It's just not Euclidean space. It's a manifold, right? So So one can check what happens in the hyperbolic case. So in fact, if we consider the Laplace operator on hyperbolic space, then using some hit kernel estimate and so on, one can check this will be the representation of, this will be the, yeah, Green's function. Then the question is, if we use this Green's function, and again the minus Laplacian of 1, 0, everything, like if we just use that their theorem to construct that W, then one can find, of course, there will be some explicit expression of W, but near infinity, that optimal W near infinity looks like this thing. Now see, what is this constant? This is Poincare constant, right? And this is some exponential decay. So exponential series means if we break it like something, some 1 of course is there, 1 over r square, 1 over r cube and so on. These kind of things will there. So near infinity somehow we can retrieve the Poincare constant. So that gives a ray of hope, like somehow Poincare inequality is still improvable. Like yes, we can, of course for Hardy it's not possible, but for the Poincare inequality we can have some hope to improve the inequality. And precisely I am asking this kind of improvement because exponential decay is there. So so now so now we need to find some W for which this operator, this is Laplacian or hyperbolic space, and this is Poincare constant. So now our interest is to find the optimal weight for this operator, because the theory of Pinchover, from their theory we can see like the Poincare case for this operator is still there is some hope. Okay, so in fact actually they're my collaborator, and they in 2017 they proved this kind of inequality, and we call it as Poincare meets Hardy, because see this is Poincare inequality and this is something Hardy type of terms. So they established this inequality, and also they told like they proved like if we consider this operator H, this operator is critical. That means this inequality is not further improvable. So that is the best possible one can expect on the improvement of Poincare inequality in this setup. And of course, this constant is Sharp constant. And what is the meaning of Sharp constant here? Like keep the Poincare term and do the ratio with this thing and take the infimum. This will be 1/4. And later, me and with Berkio and Ganguly, we proved that there are some Sharper version. Sharper version in a sense like we can replace that gradient by something radial gradient. But there is nothing like Sharper version means this contradicts the critical operator, all those things, nothing happening there. We are not improving by adding some kind of terms. We are just improving like this term. And in fact, Gauss lemma, like from Gauss lemma, due to the Gauss lemma, one can compare point-wise the radial gradient and the original gradient. So, and I want to mention our method is complete different way the proof their inequality. Okay, so we proved some Sharper version. How much time we have? Okay, so yeah, here are some more literature in that aspect, and and one can consider the family of operator also. For the family of operator with respect to Laplacian operator, Berkio, Ganguly, Grillo, and Pinchover, they give improvement. And for higher order, one can ask same kind of questions: is it possible to improve? Is it possible to have a family of inequality? Higher order means this kind of operator, and the things like that. Criticality theory is not valid for higher order case. Okay, so higher order in a sense Laplacian square, but for Laplacian, yeah, that's okay. But for Laplacian square, that's not valid. So some kind of notions of Bessel pair, which was originally introduced by Hushub and Muradi from using that notions, we answered these questions like for the higher order case. Okay, so and another interesting thing is we answered for P equals to 2, but if we see the P Poincaré inequality, LP Poincaré inequality, those things, improvement of all those things, very, very open, like how to find the improvement, how to add some positive terms, we don't know. So one can easily work there. Okay, so let me finish by giving some answer towards a conjecture. Okay, so in 2017, in the same paper, they established the improvement of Poincaré, like I mentioned, Poincaré meets Hardy, that inequality. So they proved this kind of inequality. This is some kind of higher order Poincaré. Okay, so here is Laplacian and here is U square, and this constant is base constant. Like we cannot replace this constant by something bigger one. So they proved like this kind of inequality holds, and they prescribe a conjecture like this 9 by 16 is the best constant. And again, what is the best constant meaning here? Keep this term, take minus of this term, where this is the best possible constant. We are not doing anything with the best constant. So the question is, if we take this ratio, then this will be the 9 by 16, the infimum. They told like this ratio will be exactly 9 over 16. But we proved a different kind of inequality. And see, if we have this kind of inequality, then when we'll use this inequality and we'll take the ratio, just take infimum that side. So that will be always greater or equals to 9 n minus 4 over 16, right? When we have this kind of inequality. But one can easily notice that when dimension starts 8 onwards, then n minus 4 square over 16, which is bigger than 9 by 16. So 9 by 16 is not the best constant. But I don't know, like we don't know what is the best constant. That part is still unknown, and I will say like very challenging, but interesting also. So that's all. Thank you for your attention.
Thank you very much, Prasun. Maybe some questions, comments?
Yes. Can you please go to page 5? I want to see what you have for the potential. Yeah. So, you say there is no potential.
Yeah, uninterrupted. No, like non-negative potential.
Mm-hmm. But if you, sorry, maybe I don't see something, but if you take V like 1 over the modulus of x squared plus something.
Yes, but you need to prove it.
No, but I mean, you say there is no.
There is no that kind of, yeah.
For the plane,
R2, yes, for the plane, yeah. 2-dimensional, not for RN.
Ah, okay.
RN case is there.
Okay, I see.
And the things, the criticality theory says that we cannot add further here, like on internal.
Yes, okay. For me, anyway, I'm being interested.
Another question, comment? I have one. Do you consider different operators? I mean, not like a Laplacian, but different.
Yes. Like for Laplacian, yes, criticality theory validates. And
For more general?
for more general, in a sense, I just mentioned quickly there in the reference part. We consider again this is Laplacian and this is something family. Here they proved, or actually I would say they wrote this paper inspired from criticality theory, using criticality theory arguments. But we consider this kind of operator, Laplacian square, where the criticality theory is not true. So we got help from Bessel pair, that kind of things to give answer.
You also were saying like there is some like in Hardy you can apply, in Poincaré you can do something, in Hardy no. But how do you realize like you can do something there, or it's just
In the
try to
Poincaré?
see? Yes.
Yeah.
You just try and see what happened, or there is a...
Yeah. So yeah. So the theory of Pinchot, that big theory which I mentioned here, if we apply everything for the hyperbolic setup, if we have the Euclidean case, yes, we can explicitly calculate that W, which is nothing but the Hardy weight with the constant and everything. But if we apply this Green's function for the hyperbolic space Laplacian, then we are we know some explicit expression of W, and for that W, of course, this kind of inequality holds. But interesting point to note there, near infinity that W looks like this thing. And what is this? This is nothing but Poincare constant. So that gives the ray of hope, like yes, Poincare inequality can be improvable. Yeah.
Another question, comment?
So if maybe this applies more to P, not to the case of P estimates, but you have in the critical cases sometimes you have logarithmic terms. So
okay. So
if you don't insist on having
actually that is like when that n equals to p, like for the p case, that is I think critical Hardy inequality, and if p is less than n, then we call it the subcritical Hardy inequality. So that theory is different. Like yes, actually, if we look this paper like no, sorry. So if we look this paper, somewhere they also mentioned that critical versions also. So, but yeah, those kind of improvement for the critical Hardy inequality, those things are mentioned there. So it's adding some kind of things possible. And in recent days, like Takahashi, they have some work, something called scale invariance, all those things between the in respect to the critical Hardy inequality, all those things are there. So yeah, but of course, using the critical case for the critical situations, of course, we can have some comment also. So in this paper, they are mentioned. Actually, this is very long paper, it's more than 70 pages. I need to figure it out. Many short points are there. In fact, for one dimension also, they have give some comment. Yeah. But most interesting thing is this result.
Infinity is important here. So on bounded domains, it's not.
Yeah. Exactly. That infinity bar, that is the 1-point compactifications, like something we can get that point from the boundary of Martin kernel. All those things are there. Like taking some interior point, we need to go there in that way. So in that respect, they cut the domain in some level set and prove everything on some sub-level set. And using that, they have done. I need to still figure out that paper. Like it's
You can also do inequalities in half space, for example.
Yes.
If you have half space,
It could be interesting on the half space. Yes.
Then you have to measure distance to the boundary, but there are many results on the half space.
Yes. And in fact, I can say, like this criticality theory type of arguments has been done on Euclidean space, on graph, like on the discrete case, and now what happened on the fractional setup? That is still open. Like for fractional setup, one can start building criticality theory, and one can look the Hardy weight, Hardy constant, further improvability, all those things. That's another thing one can start there. And half space also for, of course, many things can be done.
So any other comment? If no, thanks again.
Thank you.
5 minutes, I think we can in the last talk.